share the screen and you have things
Okay.
in order.
I think you should be good to share the screen.
Okay. Let's see. Oh, I think I'm sharing the wrong screen, so give me a second. Um, okay, can you see that?
Yes, looks good here.
Okay, and you can't see like the window or the notes or anything, right?
No, just the slide.
Okay, cool. Nice, so let me know when to start. I don't know what you guys are seeing or whether you're doing anything else.
All right, I think you're good.
Okay, nice. Well, first of all, I hope everybody's having a great conference. I heard that it's a nice experience so far, and I would like to thank you for giving me the chance to present virtually in this workshop. So my talk will be about learning robust computer vision in unknown environments. This is work that we did roundabout in the past 2 years, especially my PhD student based in the University of Bonn, where I was before, Julius Rukin. I would like to acknowledge him for all the hard work he put in this topic and this stream of research that we pursue within our research group. So in today's talk, we'll focus on UAVs, which are the main platform that we work with. Obviously, I'm in the micro-aerial vehicle lab, so that gives it away. So here you can see a couple of examples of UAVs doing useful things, different missions that are offer cost-effective, timely, and safe solutions to different problems while delivering data at high levels of accuracy and resolution. But in order to make them useful, as we know, UAVs rely on computer vision algorithms to understand their environments and be able to perform useful tasks, whether it's monitoring crops or wildlife, delivering aid, or urban monitoring as well. So let's go back to the basics of computer vision. Here we see an example of the semantic segmentation CNN. Hopefully we're all familiar with that. And just a quick recap, we can see here a network which takes in an input image, RGB image, in this case, some kind of street view. It does a bunch of operations through the network, convolutions, as indicated by the different layers. And on the right, we get the output, which is a pixel-wise label for each pixel in the image. So the different colors indicate different things that we see in the image, whether it's pedestrians, road, buildings, and so on. So as we know, if we train this network really well, we can get really good performance and high quality output. So the pixel-wise output is relatively good. However, we also know that in order to make such networks perform well in a supervised learning context, we need a large amount of training data. And this is often the bottleneck when it comes to training models such as this one, because it often requires time-consuming procedures to actually generate the training data, generate many samples, and also requires typically domain expertise. So if we think about agriculture, for example, we need a human to be able to label different crops and understand what they look like. This is quite, it requires expert knowledge, and it's also quite boring for anybody that has done pixel-wise labeling. They should be familiar with that. So we want to make our life easier, and to address this, we propose a class of approaches that uses autonomous robots, especially UAVs, to collect useful data for human labeling and network training. And this way we want to improve computer vision performance in unknown environments when the training data is limited. So we're going to talk about how we can address this lack of training data by exploiting the fact that we can plan paths for the robots to move and actually collect useful data. So we want to make use of the fact that robots such as UAVs are programmable devices. We can guide them where to go next. We can make decisions, and we can collect useful training data for training our neural network and improving computer vision algorithms in the supervised learning fashion. So to get an intuition of the type of challenges that we want to address, consider a situation where we deploy a UAV in an unknown environment. And at the beginning, we want to explore the environment, assuming we don't know anything about it, such as to figure out where different plants are in this field. And then let's say we detect something interesting on the field, for example, an anomaly, a cluster of the weeds or something like this. And now we have the situation that we want to stay here and collect more images, potentially at a high resolution and lower altitude, to inspect this point more closely. Or should the UAV continue exploring the environment to the parts that it hasn't been to yet to collect more images there? And this gives a sort of flavor of the type of decision-making issue that we want to address. And specifically, we want to focus not on collecting data of certain parameters that we're monitoring in the environment, but on focusing on the training data and information which is actually useful for a neural network to learn from. And we're going to do this using the paradigm of active learning. Active learning is basically being selective about which samples we train on. So we want to pick the most useful samples to train our network to maximize performance with minimal training data. That's the basic principle. So let's see how we can build these ideas into an autonomous robot planning pipeline. Now let's say we have a UAV. It has a downward-facing camera, just like in the examples that I showed. For example, RGB camera or RGBD. Then, during a mission, the UAV carries a lightweight semantic segmentation network. It uses that to predict semantic labels and the model uncertainties in the image. These are the two images that you see over here. Then, during the mission, we take these images and we project them onto a ground, assuming we know where the UAV is. And this way we can build global maps capturing these variables. So here you can see maps corresponding to the semantics on the left and the associated uncertainty on the right, where the lighter areas indicate regions of higher uncertainty. Now, based on the model uncertainty, we plan paths for the UAV to collect the most informative training data to improve the network performance. So here, the main idea and the key contribution is that we want to leverage ideas from active learning. We want to pick examples that are highly uncertain because these represent the most difficult examples for the network and thus hold the most information value when added to the existing training set. So we go to these areas that are highly uncertain in terms of model uncertainty. Then the UAV collects images, and after the mission, we give them to a human. The human annotates them. Here you can see examples of pixel-wise labeling that can be done by a human. And we retrain the network using the selected set of useful images. And our main motivation is that by collecting images in this intelligent way, we can actually save the human resources, so save time and effort, energy on the labeling process because we were selective about which images we actually want to give to the human, and the UAV collected those autonomously. Now, this is a general framework that we propose that interweaves this idea of robot active planning, active sensing, and active learning. And here we obviously have different components in this planning framework. So we have to decide what kind of planning algorithm we're going to use. We have to think about how we're going to implement the map. And also, importantly, we need to decide on the active learning acquisition function. So how do we actually pick these uncertain images? How do we represent that mathematically? So in this project we did in 2023, you can see the citation on the bottom. We investigated each of these models and proposed different alternatives in the robotics context. And the main idea is really to bridge the gap between the field of active learning, where typically we have a static set that we select examples from, and the fact that the robot can move and be able to decide on the fly during a mission how to select these useful examples. So here's some interesting results. You can see a lot more in the paper below, but just to give you a flavor of the kind of experiments that we did. So we did this experiments on the ISPRS Potsdam dataset. It's open source and it contains images of an urban area, this Potsdam in Germany. Because it's a quite detailed orthomosaic that fortunately has all the human labels, so we're able to have access to ground truth and actually do very systematic and thorough comparisons. So here's some examples of how different planning algorithms in our framework compare against each other. So first of all, how do we interpret this complicated looking curves? So it's quite simple. On the x-axis, we have the number of images that the human should label. And on the y-axis, we have network performance. So if we have less images and high performance, the curves on the top left indicate better performance because it means that the human needed to do less work while we still got maximum performance. So to recap, the curves on the top left mean that we're doing better. And the different colors show different planning strategies. So we compare it against the baseline of coverage path planning, which is just doing a lawnmower zigzag type of path over the environment. We compare different informative planning strategies, and we can see that the strategies we developed either outperform or perform on par with the lawnmower baseline because they're effectively more to the top left. And this basically verifies that actually reasoning intelligently about which images you're going to collect in this framework allows you to collect useful images and improve network performance. And then we also had a look at the map. So we did an interesting experiment varying the mapping components. So now what we do is continuously update the prior map knowledge using our approach. And if we compare this to the previous curves, we see that now most informative planners, so the ones apart from the yellow one, are pushed up in performance now that we solidly outperform the coverage baseline. I should also mention here that in purple we have a local planner, and this is one that just moves in incremental steps from the current position and does not make use of the map. So that's why here you might see a smaller improvement for the purple one as compared to the other ones. So this way we actually show that if we have continuously updating map knowledge, so if we update the map prior, we can actually even further improve performance by making the most use of the map. Then to get more insight into our findings, we also looked at per class active learning performance for the different planners. So here you see the different classes that are found in the Potsdam dataset in the different colors. And in the dashed line, we can see the performance of the one of our global informative planners, and the solid line is the baseline, so that's the coverage planning. By looking at the curves, we can also see that the informative planner does better than the baseline for all of the classes, and this confirms that the framework can capture these complex task-dependent model uncertainties regardless of the training data support, because certain classes do appear more or less in the data set, and we also have more difficulty distinguishing them. But here we can verify consistent performance by using the informative planning framework. And then next we studied different methods of how to actually formulate this acquisition function or the objective for active learning. So as I mentioned in our framework, we guide the UAV to collect the most informative data. So this is the most uncertain data. And the question is, how do we capture this uncertainty? So we investigated different ways of doing this. So here, the different figures correspond to different planners. And then the different colors represent two different ways of extracting this uncertainty. And our goal here was for different planners to thoroughly investigate what happens when we use different uncertainty measures. So in orange, we explored the deterministic non-Bayesian objective function. So here we just look at the prediction entropy over the labels and use that to derive the uncertainty. And then we also looked at different Bayesian uncertainty measures, ensembling in the yellow, which is using an ensemble of networks and seeing how the outputs differ. And in blue, Monte Carlo dropout, which is basically switching different units in the network on and off, and then investigating the uncertainty in the output. And we can see in the results that the Bayesian uncertainty measures tend to perform better, the yellow and the blue, which confirms what we would actually expect for literature, that these are typically have better global calibration compared to non-Bayesian approaches. We can also check this qualitatively. So over here in the rows, you can see the deterministic entropy and the ensembling method, and we can see how they compare. So from left to right, we see the input and the ground truth, which we took from the data set, the prediction, the output of our network, the error with respect to the ground truth, and finally the uncertainty. So we want to check how well the uncertainty correlates to the error. So we would expect that higher error leads to higher uncertainty. And we can therefore check, if we look at the deterministic approach, that this doesn't correlate as well as with the ensembling methods, which is a justification for the results that we saw in the previous slide. And we thought these results are interesting because they essentially transfer what we know from literature and the static data sets from computer vision in the robotic context and demonstrate their applicability. And now finally, this framework that I presented still needs a human in the loop. So after each mission, we do rely on a human. We give them a bunch of images and they still have to do thorough pixel-wise labeling for each one. So the natural next question is, can we actually do better for this step? Can we make the job even easier for the human and reduce the amount of labeling that we have to do? So in a follow-up work, we kept the framework the same, but we investigated what happens when we replace this pure human labeling step with a semi-supervised learning approach. So here, the motivation is actually to reduce the amount of labeling the human has to do by using two different sources of labels. So the first still involves a human, but this time, instead of labeling everything dense in a pixel-wise fashion, we want to pick sparse labels for the human to label. So we want to only query them for specific pixels in an image. That's the first step, the labels that you see on the bottom. And then we also want to make use of the fact that we have a probabilistic semantic map that we anyways built online and extract pseudo-labels so that we can leverage this as free pseudo-labels and train the network in a self-supervised fashion. So now we have these two sources of labels, we combine them, and then we retrain the network using semi-supervised principles. And we hope that by leveraging the advantages of self-supervised and fully supervised approaches into the single framework, we can maintain the applicability of fully supervised methods while reducing the human labeling effort in active learning for robotic vision. And to get inspiration for each of these methods for deriving the sparse human labels and the self-supervised pseudo-labels, we turned to computer vision literature and did several experiments to investigate what works better in this context. So these are the results that I want to present next. So first, we focused on the human labels only, and we investigated different methods of deriving the sparse human labels in our approach. So as before, we have the exact same plot. So to recap, we plot the number of images on the x-axis against, on the y-axis, the network performance. So we're looking again, top left being better performance. So on the dashed lines, we plot some baselines. So these are fully supervised methods I presented in the first framework so that we can compare how close we get when we use different ways of selecting sparse human labels. And then in the different solid colors, we compare different state-of-the-art methods of ranking possible ways of selecting the human labels. So here we explore random selection, uncertainty, and region impurity. Region impurity essentially looks at adjacency between different image regions and tries to select areas that are on edges because they represent transitions in the image. We find that our proposed method, which is the dark blue one, that combines different elements of region impurity, random sampling, and uncertainty, reduces the performance gap further, so we can actually get quite close to the baselines. We actually match the performance of the coverage reference using only 0.6% of the human label pixels, which already represents a significant saving in terms of the human effort. So we basically use these methods to identify the key regions where the human input would be beneficial. We can check that qualitatively. So over here, I want to show you different examples of what these sparse labels actually look like. So again, you see the input ground truth, the prediction, and now the sparse labels. So these are the queries for the human. And finally, the uncertainty. And we can check that the sparse labels that we derive using this combined proposed approach correspond to areas of high uncertainty. And why is that? That's because we actually query the human where we have less information and high uncertainty, so the human's input would be extremely valuable here. So for example, over here on the bottom, if you look at the red area, we have a high uncertainty. Maybe that's quite an unrepresented class or has a lot of edge regions. And this is where we can see this cluster of sparse human labels where input would be valuable. That's it for the human labels. Then we also did the same type of analysis for the pseudo-label selection. So on these plots, we showed the same two upper bounds. So this is a coverage baseline and frontier, which is an informative planning approach from the previous work, as upper bound baselines. And then we compare different ways of generating the pseudo-labels. So just to remind you, we have a semantic map that we built using during the mission by projecting these images and predictions and the uncertainties on the global frame. And we compare different ways of extracting pseudo-labels from the semantic map. So we study how what happens when we vary the pseudo-label diversity. We also consider random pixel selection, and we also consider this distal line in the dark red, which redistributes the pseudo-labels class distribution to the true class distribution. This is an interesting approach we found from the literature. So we compare what happens when we keep the amount of human labeled pixels the same, but only change this pseudo-label generation approach. And in general, our experiments show that combining human labels with pseudo-labels improves performance over using only sparse human labels. That's this green one. So by adding pseudo-labels, we actually do get some performance improvement in general. So this justifies the reason for using the pseudo-labels in this case. And again, you might ask, what do the pseudo-labels look like? So over here, I show some examples. So now we actually interestingly get the opposite effect, where we pick pseudo-labels where we have low uncertainty, because we're pretty confident that our pseudo-labels here would be correct. So taking them from the network prediction, which doesn't introduce sort of systematic errors if we trust something that has high uncertainty and is highly likely to be incorrect, we would see that this propagates errors into our retraining framework. So we want to select pseudo-labels from the semantic map that have low uncertainty and high information value. So now I want to close this section by showing you the benefits of using the semi-supervised approach. So that's this sparse human labels plus self-supervised pseudo-labels against the two different extremes, using only human labels and using only pseudo-labels. So let's start with using only human labels. How does our approach compare? So here we investigate what happens when we add pseudo-labels against only using human labels. So the human labels are the dashed lines here, and the different colors represent different human labeling budgets. So this is the amount of pixels that the human is allowed to label. So for example, 100 is located to the left because the number of pixels the human is labeling is less, and we tend to get lower performance because we don't have the human's input as much as compared, for example, with the purple and the 2000 human labels. So by adding the pseudo labels, which is with the solid lines, we can see that we improve performance. So we push things to the top left compared against the dashed lines. And this basically confirms that by adding pseudo labels, we actually get a free improvement in performance. And we can also see over here in the dashed line on the top, I plotted the performance of a fully supervised baseline. So that's the human doing all the work. And we can check that we actually reach very close in MIOU performance with the semi-supervised approach by using only 0.6% of the human labeled of the human labels that is necessary for the fully supervised approach. And this basically corresponds to a drastically reduced human labeling effort because the semi-supervised approach requires as much as 2 magnitudes less to achieve comparable performance. So that saves the human indeed a lot of work. Then we compare against the other extreme. So we just looked at what happens when we only use human labels. The other extreme is what happens when we only use pseudo labels. So over here, we plot our semi-supervised method against using only pseudo labels. The green and purple dashed lines show the self-supervised approach alone. And then we have the solid lines, which indicate using our semi-supervised approach with different numbers of pre-training budgets and also human labeling budgets. So these are variations based on how many pixels we want the human to label and how we pre-train. So the main finding here is that for all budgets, we can actually outperform the semi-supervised approach, outperforms the self-supervised approach significantly, as indicated by the gap. Why is this? Well, even though self-supervised methods benefit from minimal labeling because the human isn't in the loop, they don't have domain-specific information. And as a result, when there is actually an error that is captured by the pseudo-labels, we don't have a chance to improve it because the human input is lacking. So these methods are inherently limited in our problem setup by the lack of knowledge and systematic prediction errors. So this basically validates that in this setup, where we have many detailed things in the environment that we want to label, we actually do need the human if we have unknown environments such as the one that we considered. So this basically is what I wanted to show you about in my presentation today. I want to present a different approach on using active planning for robots, where robots such as UAVs can be used to guide training data collection and improve computer vision models in initially unknown environments by guiding them towards regions of informative data. Then we looked at different design choices we can make in terms of the map, the planning algorithm, and the active learning acquisition function, and also in the training strategy and how we actually derive these labels. And here I also showed you that by using a semi-supervised active learning approach, by combining different methods from computer vision literature, we can minimize the human labeling effort and achieve comparable performance to fully supervised methods while overcoming the systematic pseudo-labeling errors in purely self-supervised learning in these kinds of environments. So thank you very much, and I'm happy to take any questions. Again, thanks for the opportunity to deliver this talk from the Netherlands.
Thank you very much, Marija. All right, so if anyone has any questions, I will just run around with this microphone so that you can hear you. So anyone have any questions? I think I see some online as well, so I'll go there.
Thanks for the great talk. I was curious, so I noticed on some of the like overhead plots where you show like the uncertainty and the error about the segmentation. There's some, all right, I noticed like there's like around the edges, there seems to be like there were sometimes that was the places where there was maybe like some of the most uncertainty or error. I was just curious about like intuitively, like the kind of like, are these like the important, is that like something that is important to represent? Kind of like that, yeah.
The error bars, you mean?
Specifically like the edges between like segments, between objects or different things that you're segmenting.
I suppose, so in the actual labels, right?
Right, yeah.
I suppose it depends on the application. So in the case where we actually do want high accuracy and high performance, and we really do care about, locating cars precisely, for example, and buildings in this environment, could be like a urban mapping scenario where we want detailed information about where stuff is. Then it's quite important, I would say. But I would say it depends on the use case, because if you just want a rough outline of, I don't know how many of a certain type of object there is, it may not be as important.
Yeah, makes sense. Thanks.
Sorry, while we're doing questions, we're gonna have the first speaker just start getting set up here. Do you know who you are? I have you on here. Hold on. So this is going to be meta learning online dynamics model adaptation in off-road autonomous driving. All right, sweet. All right, any other questions from the audience? Otherwise, I'll check online.
No, there's none online.
None online? Okay. All right, well, I think we've timed it perfectly. So thank you very much, Marija. Let's
Thanks.
give a round of applause.
That's great, Michelle.
Thank you for taking the time to give this talk, and yeah, it's very exciting research.
Thank you.